Hello my friends and welcome back to the Today Machine channel. The aluminum extrusion process at ILSCO Extrusions Inc. is engineered to transform recyclable, lightweight, and high-strength aluminum into precise custom profiles. Production begins with alloy-specific billets, cast in log form and cut to uniform lengths. These billets are heated in a controlled furnace to approximately 900 degrees Fahrenheit, reaching a malleable yet still solid state suitable for deformation. Simultaneously, critical tooling such as the container, die, and support components are preheated to ensure thermal consistency throughout the extrusion cycle. At the press, residual material from the previous billet is sheared, and a hydraulic ram applies thousands of tons of force, pushing the softened billet through a hardened steel die. As the aluminum flows through the die opening, it assumes the exact geometry of the designed profile. The extrudate exits the press and immediately enters a water quench system, stabilizing temperature to achieve the required mechanical properties. A synchronized puller grips the hot extrusion and guides it along the runout table, where infrared laser monitoring cameras continuously track billet temperature, press exit temperature, and quench exit temperature. These data points ensure each extrusion run remains within strict metallurgical parameters. Once cooled, the profile is cut at the billet seam, transferred across the cooling table, and passed through a stretching unit to remove internal stresses and ensure straightness. The extrusions are then cut to customer-specified lengths and placed into aging ovens for final hardening, according to alloy and temper standards. Secondary operations such as precision cutting, deburring, vibratory finishing, and surface preparation provide ready-to-coat components before packaging and delivery. At Gerdau's Duluth facility, grinding balls are produced through a tightly controlled metallurgical and forging sequence designed for uniform hardness, high wear resistance, and structural integrity. The process begins with 98% recycled scrap steel, which is sorted to achieve the proper chemical balance before charging into an electric arc furnace. Here, high-power electrodes melt the scrap into liquid steel, which is then refined in a ladle station where alloying elements are added to meet targeted mechanical properties. The molten steel is cast into continuous billets and transferred to a rolling mill. After reheating, the billets pass through precision rolling stands that generate round bars with consistent diameter and concentricity. These bars are then shipped to Duluth for forging. On arrival, bar dimensions and grade are verified before entering induction heating lines. Controlled induction coils elevate each bar to the exact forging temperature. A shear cuts the bar into predetermined lengths, which are immediately pressed between primary forging dies to form the spherical shape. Secondary rotating dies refine the geometry and remove flash. The balls then undergo air and water quenching followed by tempering to achieve final hardness. Each batch is inspected using manual checks and automated sensors before packaging for global delivery. Franchini AKI operates as a high-capacity European forging manufacturer built around a vertically integrated workflow designed for precision, metallurgical stability, and heavy-duty part performance. Production begins with certified European steel ingots, selected to meet strict chemical and structural specifications. Cutting is optimized through a bank of 20 high-power saws and an oxy-fuel station, enabling precise sizing before forging. The forging phase is supported by 10 furnaces ranging up to 450 cubic meters, capable of hot charging ingots delivered directly from steel mills. Once brought to forming temperature, ingots are processed on 3 open die presses, 2, 500, 3, 500 and 8,000 tons, each equipped with automated manipulators for controlled upsetting, stretching, mandrel piercing, and custom deformation sequences. This setup allows handling of pieces up to 100 tons with consistent strain distribution. Heat treatment is performed in rail-mounted furnaces, reaching 150 degrees Celsius, paired with quench tanks fitted with variable speed propellers to regulate agitation for water or polymer media. The system accommodates components up to 24 meters in length, using automated loaders to manage multi-piece treatment cycles with accurate transfer timing. Post-treatment machining utilizes CNC vertical and horizontal lathes, milling machines, borers, and deep drilling equipment for both roughing and final finishing. Quality control integrates magnetic particle and dye-penetrant surface inspection, ultrasonic internal testing, dimensional gauging, and Brinell hardness evaluation. Additional capabilities include heat stability testing for rotors up to 50 tons and destructive mechanical testing in an in-house laboratory. This technical infrastructure supports the production of critical components for energy, oil and gas, naval, nuclear, and heavy engineering applications. The Albabtain Melipole manufacturing facility operates as a fully integrated production plant, specializing in high-strength steel poles for power transmission, lighting, and telecommunication networks. The process begins with the selection of certified steel coils, which are fed into automated CNC slitting and plate cutting lines to achieve precise panel dimensions. Each plate is then formed on programmable bending machines, creating tapered or polygonal pole segments with consistent geometry. Longitudinal welding is performed using advanced submerged arc welding systems that guarantee deep penetration and uniform bead formation along the full seam length. Weld integrity is verified through ultrasonic and radiographic examination. After welding, the sections undergo calibration in hydraulic press machines to ensure straightness and dimensional accuracy. Pole segments are then fitted, rechecked for alignment, and processed for door openings, baseplate installation, and attachment of accessories using robotic plasma or oxy-fuel cutting equipment. Galvanizing is conducted in a large hot-dip zinc bath, where the components are chemically cleaned, flux-treated, and immersed to achieve corrosion-resistant coating thickness according to international standards such as ASTM 123. Post-galvanizing, each pole is inspected for coating adhesion, thickness, and surface continuity before entering final assembly and bundling. The facility's controlled workflow ensures high structural reliability and long-term durability for infrastructure applications in demanding environments. The steel pole manufacturing process at Melipole starts with a paper design, which is then transferred to CAD software by engineers to create detailed technical drawings. Based on the design, steel plates are precisely cut using CNC machines or by hand, ensuring the required size and shape. The pre-cut steel plates are then bent into cylinders, shaping the poles using hydraulic bending machines or specialized mechanical equipment. Joints and special details are hand-welded by skilled workers, ensuring durability and aesthetics. After welding, the poles undergo quality checks for straightness, dimensions, and welds, before being surface finished and prepared for shipment. This process ensures that Melipole steel poles meet high technical standards and durability in all applications. Finally, the lighting poles are completed for installation of lighting systems, ready for street, park, and urban projects, ensuring safety and optimal lighting efficiency. The CKD production plant handles components weighing up to 240 tons and with diameters up to 15 meters. Welding processes include manual, semi-automatic, and fully automatic methods, all compliant with EN, DIN, and ASTM standards. Certified quality control is conducted using dye-penetrant, magnetic particle, ultrasonic, and X-ray testing. Heat treatment is applied for stress relief of welded structures and castings. Component dimensions reach up to 6,400 x 3,600 x 12,400 millimeters, with weights up to 100 tons. Vertical boring and turning, milling, cylindrical and flat grinding, and CNC machining centers ensure high precision. Finished products are packaged in sealed, heat-resistant film and prioritized for maritime container transport. CKD ILSCO specializes in small hydro solutions with high efficiency, integrating state-of-the-art technology across all stages of design and production. The process begins with basic and detailed design at the Water Machinery Research Institute, ensuring that each turbine meets exacting performance standards. CKD ILSCO manufactures a wide range of runners, including Pelton, Francis, and Kaplan types, tailored for varying heads, outputs, and runner diameters. Francis turbines cover heads from 10 to 300 meters, outputs from 200 to over 40,000 kW, and runner diameters between 400 and 1,700 plus millimeter. Kaplan turbines operate at heads of 2 to 40 meters, outputs from 200 to 10,000 plus kW, and runner diameters of 500 minus 3,000 plus millimeter. Pelton runners handle high head applications from 70 to 800 meters, with outputs up to 40,000 plus kW, and runner diameters ranging from 400 to 3,000 plus millimeter. Precision manufacturing is achieved through highly accurate welding and machining processes, with comprehensive shop assembly ensuring seamless integration. Hydromechanical equipment includes slide gates, stop logs, trash racks, cleaning machines, and main inlet valves to manage water flow and ensure reliability. The electrical system features digital governors, advanced control and protection systems, and low, medium, and high voltage equipment to guarantee safe and efficient energy conversion. CKD ILSCO combines meticulous engineering, advanced technology, and rigorous quality control to deliver hydro turbines and associated systems capable of operating efficiently in diverse hydraulic conditions, providing reliable, renewable energy solutions worldwide. A tool and die maker is a highly skilled professional who designs, builds, and maintains the tooling used to produce finished parts. They work across various manufacturing processes, including die casting, plastic injection molding, stamping, forging, and jig and fixture creation. Their role combines precision machining, assembly, and project management, often using CNC machines, surface grinders, EDM, and CAD/3D software. Apprenticeships require approximately 400 hours of paid, on-the-job training, plus technical coursework. Tool and die makers ensure parts meet specifications, optimize production, and can specialize in areas like CNC machining, offering a high-tech, long-term career in advanced manufacturing. At the grand opening of Global Hydro, the new facility marks a major advancement in sustainable energy technology. Central to operations is the Reedon RX-14, a cutting-edge 5-axis machining center engineered for precision and heavy-duty performance. Capable of handling workpieces up to 14 meters in length and 12 tons in weight, the RX-14 delivers accuracy within plus or minus 0.02 millimeters. Its high-speed spindle reaches 20,000 revolutions per minute, enabling flawless machining of turbine components, impellers, and large hydraulic assemblies. Live demonstrations highlighted the RX-14's automatic tool changer, intelligent control system, and modular setup, showcasing versatility and advanced engineering. Efficiency is enhanced while minimizing material waste and energy consumption, supporting Global Hydro's commitment to environmentally responsible solutions. Global Hydro's launch reflects a strong vision for the future, positioning the company as a leader in water technology and sustainable infrastructure development worldwide. For some, hydropower is just a form of energy. For Flavel Energy, it is a path to a sustainable future. Turbines, generators, and control systems are designed for optimal hydraulic efficiency, high reliability, and minimal energy loss. Each component undergoes rigorous quality control, ensuring alignment, balance, and mechanical integrity for sustained operation. Intelligent automation and modular designs enable seamless integration, adaptive control, and simplified maintenance. State-of-the-art manufacturing facilities produce components to the highest international standards, supporting small and medium hydro projects worldwide. Water-to-wire solutions combine high-performance energy conversion with durable materials, advanced monitoring, and robust safety systems. Graphite India Limited manufactures high-performance graphite components using synthetic fiber raw materials produced via extrusion units located in Durgapur, West Bengal. The facilities are equipped with CNC vertical turning machines, hydraulic presses, vertical tube assembly lines, cutting machines, and precision testing fixtures to ensure high accuracy and consistent quality. Components undergo rigorous inspection, including leak tests, dimensional verification, and impregnation processes, ensuring suitability for chemical and industrial applications. Careful handling during assembly and automated inspection minimizes defects and guarantees operator safety. Standardized graphite rods, tubes, and custom components are produced with attention to mechanical stability, long service life, and chemical resistance. All processes, from machining to assembly and quality assurance, follow ISO-certified procedures. Advanced monitoring, calibration, and precision tools maintain consistency, while modular and scalable setups allow efficient production. This engineering-driven approach ensures that graphite components deliver reliable, durable performance in industrial equipment, chemical reactors, and specialized engineering applications. Interpipe Steel is a modern electric steelmaking plant producing billets for pipe and wheel manufacturing. Electric arc furnaces melt scrap metal, followed by continuous casting machines forming precise billets. CNC machining, hydraulic presses, and vertical assembly units ensure dimensional accuracy and mechanical integrity. Advanced gas cleaning systems minimize emissions, while rigorous quality control and testing guarantee long-term reliability, energy efficiency, and compliance with international metallurgical and environmental standards. The wire drawing operation handles low-carbon steel at a production rate of 700 tons per month. Steel rods are fed into high-precision drawing machines, reducing the diameter through sequential dies while maintaining surface quality and tensile strength. Wire is drawn at speeds up to 21 meters per second, ensuring uniform elongation and mechanical properties. Continuous lubrication and controlled tension prevent surface defects and material fatigue. Advanced monitoring systems track speed, tension, and temperature throughout the process. Post-drawing, wires undergo annealing, inspection, and spooling to ensure dimensional accuracy and compliance with metallurgical standards. This operation combines high-speed automation, precision engineering, and quality control, delivering consistent, high-performance, low-carbon steel wire for industrial applications. The add-do-feed solution provides a small-diameter, high-feed milling cutter designed for expanded application coverage, with cutter bodies as small as 8 millimeters. Utilizing negative inserts and fine-pitch threads, the cutter achieves high tool rigidity, despite its compact size. Miniaturized inserts enable a multi-flute design, combining high rigidity with multiple cutting edges for efficient material removal. The design supports high-feed machining in restricted spaces while maintaining precision and surface quality. Add-do-feed delivers enhanced stability, extended tool life, and versatile application, making it suitable for demanding milling operations in aerospace, automotive, and general precision engineering sectors. Aleris Rolled Products in the USA features a high-bay storage system designed for efficient handling and storage of aluminum coils. The system accommodates 504 coils, each weighing up to 26.5 tons, with automated infeed and retrieval via 2 high-speed stacker cranes. These cranes operate at a horizontal speed of 180 meters per minute and a vertical speed of 24 meters per minute, enabling rapid transfer to the cold rolling mill and inspection stations. The system includes automatic strapping and marking, as well as smooth return of coils to the high bay store. Engineered for high flexibility, the storage solution handles sensitive aluminum coils extremely gently, reducing the risk of damage. The intermediate storage system efficiently connects different processing lines, providing a cost-effective solution for production continuity. Conveyor systems integrate seamlessly with the storage racks, supporting temporary coil storage between process steps. Advanced warehouse management features, including temperature monitoring, ensure coil quality during storage. The system is future-ready, designed for easy expansion by an additional 200 storage positions without structural modifications. This high-bay storage system exemplifies precision engineering, operational efficiency, and gentle material handling in modern aluminum processing facilities. Drillmeister head-changeable drills deliver stable performance, extended tool life, and cost savings by eliminating tool reconditioning and reducing inventory. One-action head replacement improves reliability and prevents accidental head detachment. High concentricity ensures precise machining, while the proprietary chisel design provides exceptional cutting engagement. Dual margin features stabilize head movement, maintaining consistent performance. These drills offer unparalleled efficiency and durability, making them ideal for demanding applications where precision, reliability, and reduced operational costs are critical. Jyoti Americas operates a lattice transmission tower manufacturing facility in Conroe, Texas, where every stage of production is supported by advanced automation and engineering precision. The in-house Engineering Center of Excellence oversees structural design, while fully automated fabrication systems minimize material handling and ensure dimensional accuracy throughout the workflow. Steel plates are processed using multifunction plasma arc fabrication equipment, delivering consistent cutting quality for high-load tower components. Structural members are further formed through custom die-pressed hot bending, producing uniform mechanical strength and reliable geometric stability. The in-house quality laboratory conducts continuous inspections, monitoring weld integrity, mechanical properties, and overall compliance with tower specifications. The galvanizing line represents one of the most environmentally friendly systems in the industry. All fumes are captured by an advanced air processing unit, while the fully enclosed, negatively pressurized pre-treatment building prevents emissions during chemical preparation. The galvanizing kettle operates at a controlled 450 degrees C, creating a durable, corrosion-resistant coating essential for long-term field performance. Completed tower components are bundled tower-wise and prepared for efficient transport, ensuring seamless integration into North America's electrical transmission infrastructure. High-speed spring production at 110 springs per minute relies on precisely drawn low-carbon wire, engineered for consistent elasticity and surface quality. The wire is processed through multi-stage drawing dies to achieve tight dimensional tolerances, stable tensile strength, and superior straightness, critical for rapid coiling. A high-speed spring former synchronizes feeding, coiling, cutting, and pitch control through servo-driven mechanisms, ensuring repeatable geometry, even at elevated throughput. Advanced lubrication and cooling prevent heat buildup during shaping, while real-time sensors monitor wire tension and detect deviations instantly. This combination of precision wire drawing and automated forming delivers uniform springs at maximum production efficiency. Hot-dip galvanizing is a metallurgical process that protects steel by forming a permanent zinc-iron alloy coating. After steel is cleaned through degreasing, acid pickling, and fluxing, it is immersed in molten zinc, where a chemical reaction creates multiple intermetallic layers topped with pure zinc. These layers are harder than the base steel, delivering exceptional abrasion resistance and long-term structural durability. Zinc's slow oxidation rate enables the formation of a stable carbonate film, while its galvanic action prevents corrosion from spreading when scratches occur. Because zinc sacrifices itself to protect exposed steel, the coating delivers decades of maintenance-free service, even in aggressive environments. Highly recyclable and energy-efficient, galvanizing remains one of the most sustainable and cost-effective corrosion protection methods in modern construction and heavy industry. Metal cutting with an oxygen lance is a high-temperature process used to sever extremely thick or refractory metals that conventional torches and mechanical tools cannot penetrate. The system operates by feeding pure oxygen through a steel pipe or consumable lance tube, while the workpiece is preheated to ignition temperature using an auxiliary torch. Once the metal surface reaches a critical heat level, the oxygen stream initiates rapid oxidation, generating exothermic energy that melts and burns through the material. The reaction temperature can exceed 3,000 degrees Celsius, allowing the lance to cut cast steel, high alloy components, reinforced concrete, or slag-contaminated structures with remarkable speed. As the lance burns, its tip continuously oxidizes, enabling deep penetration and controlled kerf formation. Operators regulate oxygen pressure to maintain a stable cutting front and ensure uniform removal of molten oxide. In industrial applications, oxygen lancing is used for dismantling heavy equipment, opening furnace taps, cutting oversized scrap, and performing emergency interventions where access is limited. The process demands strict safety controls, including heat-resistant PPE, backflow prevention, and careful handling of molten debris. When executed correctly, oxygen lancing delivers a powerful and highly flexible solution for extreme metal cutting conditions.